stat. Get you in the neighborhood.
Well, and off of those things, those calculators, I draw out like atomic.
So find that number.
Right. Right. Pretty badass. Audra, go, please.
So say it's like 400 and then 400 plus.
The percentage of something.
Let's regroup. Yes, go ahead. Go ahead.
More friends than he does.
Answer this question right here. Let's answer that question together. I want to regroup, friends. Let's regroup.
We're gonna go through it. Yeah. I'm wrong.
Let's regroup. I want to make sure we're happy with these solutions. Yes? We're happy. I want y'all to get tens.
We're argumentative.
But I also want you to make sure that you're happy with these. You understand why I'm making you do all this. It seems like an awful lot of hoops I'm running through. I'm making you run through. I make you calculate the average. I make you calculate the standard deviation, and then I tell you to write down we shouldn't use it. That seems like a waste of time, except it's not a waste of time. Because in general, what you would have done first was, you would have graphed the distribution. And you would have said, oh, it's skewed. Let's not bother finding the average and the standard deviation because it's skewed. See, does that make sense? And again, I'm leaning a little bit towards 244 here by doing this, by kind of making that lean. But that's what statistics is all about. Here's a bunch of tools. Which ones make sense for the situation I'm in right now? So that's how you learn. You learn by saying, oh, I shouldn't use that because the average is pulling to the outliers. So we pull back and we say, all right, let's look at percentage-wise. So I think we know what the answer to that one question is. What percentage of friends in my sample have more than 673 friends? 22%. Everybody happy with that? 13 divided by 60? I'm happy with that. Okay, then I tell you, based on that sample of size 60, you should have a margin of error of 10% on that 22. Why? First of all, I know we know how to calculate that, because if you apply a 10% margin to 22%, what do you then have? You have a range of values between
12 and 32.
12% up to 32. Can you give me a percentage that's in that range? Make up one. 24.
69.
24. Give me another one. 13's in there, right? It's right above 12. 14. 31. Right? Give me one that's out of that range.
47.
47's out of that range. Or 50. Or 60. Or 10. 10's too low to be out of that range. Please, Trinity.
Just how did you get the margin?
Again, it's based on a calculation. The quick and easy answer. You ready for this, Taryn? Quick and easy answer. 0.22 times 0.78 divided by 60, square root of the whole thing times 2. Now, you will know why that is that as we go. No, God, don't write that down. And we're going to be developing that as we go through the course. Trinity asks a very good question. All of a sudden, this magical 10% drops in your lap. The reason I did that is because of Malcolm Gladwell's book that I read over the summer that says the way something is truly learned in classrooms is to repeat it at least 7 times. So what I figured, if I can keep getting you guys applying margins of error to things, while we're learning how to build them, you'll know how to use them after you know how to build them at the end. You already have a gut feeling. But that's a better question is, why do you even need it? Why do you even need to put a margin of error on your calculation? Whether it's 10% or 15% or whatever it is, Riley? Because I didn't use my entire population, right? I drew a sample from a population, which means, am I 100% sure? No, I probably have a little bit of offness to counter. And the offness is countered by the margin of error. Error is not a bad thing. Error is something you have to live with. You have to live with the error because the error is a function of the fact that you didn't check every single person. You only checked a sample. You have to put a plus or minus on there. Let me test the waters for how we're feeling intuitively. Suppose instead of 60 people, I did 600 people. It would be a little more work as far as pulling the data.
The margin of error would be smaller.
The margin of error has to be?
Smaller.
Exactly, because you're probably going to be less in error then, right?
You have more of a bigger sample.
Perfectly said. Perfectly said. So, but based on a sample size of 60 though, it's got to be plus or minus 10, which is actually pretty wide if you think about it. That's a lot of percentage up. Please, Faith, go ahead.
So then when you're looking at any kind of statistic, the main thing you want to know is what the margin is.
You have to know what that is, otherwise everything is meaningless. When they tell me things, well, for example, I was trying to see if I could believe the line, your friends have more friends than you do. I was trying, the whole point of this, you probably forgot that already, didn't you? Like, you made us do a whole bunch of math. What was the whole point of doing all this crap? Was because I wanted to test the claim, the validity of your friends on average have more friends than you do. Now, number one, their average of 470 was less than my 673. But then we said that, which is the opposite of the claim, right? But I threw that out because the average looked wrong to me. So then I said, let's check percentage-wise. Well, if percentage-wise it would hold up, what percentage would we have to be seeing if my friends have more friends than I do on average? This is a bit of a tricky question, but Alicia?
Would it be over 50?
Over half would be a majority, right? Over half. So when I get 22%, I put my hands up and I go, I got it, and then I go, oh, wait a minute. It's not exactly 22. I have to check the margin too. But even when I slap a margin on there, what's the most it gets to? 32. 32, which is still below 50%. So once again, I go, I don't believe the article. I just found a counterexample. That's the power, though. It gives you that refinement of saying, oh yeah, you got 22%, but it's plus or minus. Now, if the plus or minus was too big, it might get to the point where we can't disprove it. Suppose the plus or minus was, like, just to make up a ridiculous number, 40%. Well, then that 22 would go up to 62, which is above 50, and then you put your hands up and go, I got no. But, I mean, if you ever, or negative on the other end, which doesn't make any sense, right? But you're not going to see margins that are that big unless you're sampling like 3 people. In which case, please don't do that. If you ever have to do a sample, just come talk about proper methodologies. And we do it in 244 as well, as far as proper methodologies. But that's the idea. It's just more tools in the toolbox. How to deal with this data. How to read something. Here's one I'm going to have you guys attack later on in this course. Somebody sent me, a former 243 student sent me a Facebook post. It was one of those things, 21 things you can't believe about mathematics. Every time you shuffle a deck of cards, the order those cards that you get is in has never been seen before, ever.
What?
So take a deck of cards, shuffle it. Every single time you shuffle a deck of cards, the order of those 52 cards is in an order that has never ever happened before. I think it's believable.
Really?
I ran the numbers last night. I think it's believable.
That would be infinity then.
No, it's not infinity. It's 52 bang, which is pretty damn big, but not infinity. But this is this is the thing though. You see how you guys are like, no, that can't be right. Wait, I don't know. Corey, what's on your mind?
Well, isn't that like 1 times 2 times 3 times 4?
Up to 52? Yes, sir.
Yeah.
It's a huge freaking number when you multiply them all out. You've got a whole project devoted to just that idea. But I want to turn that... And Andrea's like, no, I should have taken the other professor. But the idea is, I can't guarantee that if Faith takes a brand new deck of cards and shuffles it, and I do, that we don't get the exact same thing.
Because clumping still happens.
The clumping still happens, but my idea is when you look at the randomness of how many possibilities there are, and compare it to something concrete like the believed age of the universe, it's crazy. But this class gives you the tools to read that and be able to say, I don't know the answer, but I bet you I can take a crack at it and try to figure it out. So that's the thing. That's where this came from. Somebody said, your friends have more friends than you. I'm like, really? Okay, let's see. I love that. Let's see. Let's see if we can believe that claim, or let's see if we can refute that claim. I refuted it. But that doesn't mean that it doesn't hold for other people. I'd love to see more data. If you guys want to crack down some of your own data and send it to me, we can analyze it as a class too. I can make a quiz out of it if you ever want to do that. So if you ever want to get me data like this off your Facebook page and you don't mind, send it in. I'll make it anonymous, of course. I love that though. I love being able to take this and just put it to something that just gets sent to me, or, you know, Instagram. It was an Instagram message last night. That's where that shuffle cards thing came in. But Corey, that was the solution I used right there, what you just mentioned. And it's staggering. We'll get to it.
Pretty big statement to say never.
It is, but probabilistically I believe it. Statistically, probabilistically, and randomly, I do believe it. We'll see why as we go through the course. But my bigger picture is being able to apply these methods to something that you encounter in your life. You'd be amazed when you shuffle a deck of cards how many different shuffles there are. You can't probably perceive in your mind right now. Take a guess. If you took a deck of cards and shuffled it, how many different possibilities? Throw some numbers out.
A lot.
Well, give me a lot. Give me a lot.
A million.
A million. Love it. That's a big number. A million. Yeah. Some other numbers.
86 trillion.
86 trillion. 86 trillion. If you don't mind.
Have at it.
Other ideas. Come on, keep them coming.
Is it in the quintillions?
I saw that. Was like, wait a minute, what?
I don't know. Jason, go.
I'm going to say
Because Google is like a number, and I think it was to a certain,
It's not quite that.
not a Google.
But what is a Google in alien form? I don't actually know the answer to that question. I haven't figured it out. So just so you know, the number of arrangements is 4.5 times 10 to the 66th power. Now, a million is 10 to the 6th. A trillion is 10 to the 12th. This is 10 to the 12th to the 5th, but even bigger than that. So it's trillions of trillions of trillions of trillions of trillions and a million of those. So, I mean, do you see whose heads are going like at this point, right? It's a little, right, it's a little hard to process because it's so freaking big because it's super exponential growth. It's exponential growth in 105, but like on steroids. So, we'll get to it. We've got to it right now, kind of, inadvertently, but the idea is we can apply what we're learning right now to that, and we'll deal with it. And take time, Andre. I don't want to upset anybody. Fair? So yeah, trillions of trillions of trillions of trillions of trillions and a million of those. And it's kind of hard to think about, because then you're like, okay, now we're talking about like counting the sands on a beach kind of thing, or counting the hairs on the head kind of thing. It gets all biblical. And it's crazy to think about that way, right? Oh, makes me all happy.